morning. Thank you for joining us today. My name is Kate Clavon. I am a lead water resources engineer with Stantec down in Colorado Springs. I'll be presenting today with one of our lead restoration designers, TC Dinkins, who sits up in Fort Collins. Now, us over here at Stantec are actually really excited to share with you a creek restoration we're quite proud of. This is a project that we completed with the City of Aurora. It encompasses 3 reaches and almost 2 miles of channel. We started design on this project in 2017 and construction wrapped up last year. So please sit back and we hope you enjoy your tour of Tollgate Creek. So what makes Tollgate Creek so interesting? Well, like many of our urban channels on the Front Range, the storm flows that this creek sees are quite flashy. Here we'll zoom in on Tollgate Creek over in Aurora. As you can see, this is a developed watershed. It is 50% impervious area. This gives us high flow rates. If we look at the 100-year discharge, our project is over 20,000 CFS. Now, as a comparison, let's look at a rural watershed most of us are familiar with, Big Thompson River. The Big Thompson River at Cedar Cove is a watershed that is 10 times greater than Tollgate Creek. But when we compare the discharges, the 50-year storm flow for Tollgate is greater than the 100-year flow of Big Thompson.
Another issue we see in many of our urban Front Range channels is a sediment imbalance. As part of our assessment of Tollgate, Stantec performed a banks assessment to quantify the channel erosion. This assessment estimated that the combined project reaches were losing over 2,000 tons of sediment a year. The soils at this site were variable, but mostly consisted of subsurface sand and silty sand soils with a higher clay content found near the surface. Not surprisingly, given the increased frequency and magnitudes of flows and the sediment imbalance, this is not a stable system. Here's a diagram we're all familiar with, showing the common evolutionary model of stream succession. The valley in our project area is unconfined alluvial. This valley type commonly includes meandering riffle pool stream systems within a well-developed floodplain. However, in the pre-construction condition, we observed mainly Roskin type F and G channels. These are highly entrenched channels, some with width to depth ratios less than 8. What this means is we are working with a system that historically had a 300-foot floodplain and a channel cross-sectional area of 85 square feet. But our pre-construction channel cross-sectional area was more than 3 times this historic channel. This means that the 5-year storm event was trapped inside these gullies, a typical situation in the stage 3 and 4 of the channel evolutionary model. The final point I want to touch on before handing it over to TC is to talk about the floodplain. Remember the flows of the 50-year and 100-year storm events? Well, the result of having these high magnitude storms means that despite the entrenchment of the system, we still have 37 residences along the corridor that were located within the 100-year floodplain. The special flood hazard area along Tollgate consists primarily of Zone AE, so work in the channel required a kilometer to FEMA to reflect those proposed changes. And now I'd like to introduce TC Dinkins. TC's been with Stantec for over 10 years, and he's been working with the City of Aurora since 2015 on this project. He led the overall watershed study, which originally identified Tollgate Creek as a priority area for restoration. He was the lead designer on the project and often on site during construction. TC is going to walk through the origin of how the project came to be, our design approach, and then the much promised virtual tour of the site. TC?
Thanks, Kate, for the introduction, and thanks to all of you guys for joining us this morning. Like Kate said, I've been working on this system for over 6 years, and I'm excited to finally present the full spectrum of this project to all of you. The Tollgate Creek Confluence Project came to fruition as a result of a large drainage basin study conducted by Stantec for the City of Aurora. The city was interested in the qualitative assessment of existing conditions of all channels and drainages within city limits and the identification of priority reaches. Sediment loading to the South Platte watershed due to channel erosional processes is a widespread problem from both a channel health function standpoint and channel maintenance. This assessment was a large undertaking as there were over 170 miles of channel within city limits, including the 22 main stem channels listed here. Stantec utilized high-resolution orthophotography, a comparison of 2008 and 2013 LiDAR DEMs, and a bank slope analysis to identify priority areas of aggradation, degradation, and exposed channel banks. The results of the desktop analysis were colorized into a comprehensive map book that provided a visual representation of both changes in channel base levels and erosion-prone banks. The channels near the Tollgate Creek confluence were some of the most impaired reaches identified in the desktop analysis, which were major contributors to sediment loading and the threatening of existing infrastructure, including a stormwater outlet apron that was hanging at least 5 feet above the bed. The team conducted geomorphic surveys at the highest rated priority areas. As Kate alluded to earlier, this included non-point source bank erosion rates using the Banks model to estimate reach-specific annual sediment contributions due to bank erosion. These field verification results were used to further trim down the highest priority reaches. The West Tollgate Creek and the Tollgate Creek in the vicinity of the Peninsula Townhomes were 2 of the 4 highest priority reaches. In addition to the instability concerns of the channel and these reaches, updated floodplain mapping from the master drainage plans conducted by others showed inundation of private properties due to spill flow from East Tollgate Creek. All in all, this area was in bad shape, and the city decided to tackle these problems head on, and thus the Tollgate Confluence Channel Improvements Project was born. We worked with the city to develop a list of objectives. Kate has already touched on the first 2, and I'm going to dive a little bit into the next 2. The state of the channel and riparian conditions were a big concern. For example, the wetlands throughout the site were showing signs of active deterioration. Due to the duration of the initial phases of the project, 2 independent wetland delineation surveys were conducted in 2016 and in 2017, which showed a reduction in wetland area by 10%. This can likely be attributed to the degree of channel incision and the elevation difference between the baseflow and historic floodplain. The vertical channel banks and incised channels were typical throughout the site, which disconnected local residents. Previous attempts weren't going to work. The recommended approaches in the existing major drainage way plans were only focused on alleviating flooding concerns, but didn't address the ongoing channel function degradation or potential long-term maintenance requirements. A previous bank stabilization project along West Tollgate Creek had utilized a grouted boulder toe without addressing channel dimensions. While the approach did provide stability along the treated bank, it simply moved the problem downstream and resulted in further bank erosion. Stantec's design set out to serve as a more comprehensive solution to the many challenges present within this project area. So let's get on to the fun stuff and introduce you to the project site. Our Civil 3D design file will serve as our guide to orient us about the site. East Tollgate Creek and West Tollgate Creek come together to form Tollgate Creek. We're going to start our tour at the new confluence. In the background and to the right, the neighborhood called the Peninsula Townhomes were aptly named as they were located on a narrow strip of land between 2 tributaries. We are hovering over the new confluence, which was designed such that the reconnected floodplains redirected the tributaries' overbank flow in a down valley direction. This confluence is located about 110 feet north of the previous confluence, which was located just between these 2 trees here. And if you remember the hanging culvert that we showed earlier, this whole channel has downcut by about 5 feet since previous conditions. The downcutting and bank erosion was threatening existing infrastructure adjacent to the channel. Around the same time as the inception of this project, one of the project partners, Mile High Flood District, had been planning a project with Olson Associates to stabilize the unstable valley wall at the pre-project confluence to protect a large sanitary sewer line and other existing infrastructure. The City of Aurora and Mile High teamed together to incorporate both project objectives and Olson joined our team and provided engineering consulting services for the drop structure design. Let's travel up the new East Tollgate Creek corridor. The pre-project East Tollgate Creek channel through this area was narrow with near vertical banks. Opening up this valley to gain the flood flow capacity necessary to eliminate the spill flow required the excavation of a lot of dirt. Estimated at over 110,000 cubic yards of excavation, the grading design was optimized to balance the cut fill on site without requiring haul off. We literally moved mountains to create these newly connected channels and floodplains to adequately convey the 100-year flows. The channel restoration project also had to coordinate design and implementation of a new 10,000 plus foot City of Aurora Parks and Recreation open space regional trail system that involved a low water crossing across East Tollgate Creek. This crossing provided new and safe access across Tollgate Creek to the public. The channels and floodplains were designed based on the drastically variable flow conditions that are typical of this watershed. This high-functioning and low-maintenance design approach utilizes multi-stage channels to accommodate low-moderate flows, moderate-high flows, and the extremely large flow events. One of the primary challenges to successful restoration in our semi-arid climate is the speed in which revegetation grows after the completion of land disturbance. On a site like this, where a newly constructed floodplain is likely to see overbank flows in the first months or years following construction, floodplain scour is a major concern. Unlike other typical civil projects, channel restoration projects are at their most prone state right after construction, but get more robust and resilient with time as vegetation is established. And to mitigate for potential floodplain erosion in those first couple of years, we implemented a bioengineered structure that I call a floodplain brush sill. These sills consist of both live cuttings of willow and cottonwood poles and excess brush material that is trenched into the floodplain adjacent to the bankfill channel. The live cuttings are installed in a manner that provides access to groundwater, which expedites the revegetation timeline. They are intended to emulate natural floodplain roughness that occur in more mature floodplain margins, which can slow down the overbank flows and reduces the potential for erosion. The geomorphic-based design approach created a more diverse channel bed form by establishing a riffle and pool morphology. We primarily utilized low magnitude and more frequent riffle structures to create a stable profile and spread the channel gradients over a longer distance. One of the riffle grade control structures that we utilize throughout this project is a void-filled riprap and brush riffle. These structures utilize well-sorted natural stones with lifts of woody debris installed in a manner that provides both a sub-base structural stability and an increase in surface roughness. The slight protrusion of the woody debris helps to slow the water down as it passes over the riffle. At the upstream end of East Tollgate Creek Reach 2, the localized site conditions required a more robust structure to accommodate the drop in channel elevation of over 3 feet. This structure, designed by Olson Associates, utilized void-filled riprap and large boulders that were not grouted in place. A concrete capped sheet pile wall was installed along the front face of the structure to prevent seepage beneath it. Building these structures without grout allows for vegetation to occur along the margins and helps them to blend in with the surrounding landscape. Additionally, a more traditional grouted boulder drop structure, also designed by Olson, was needed in the Tollgate Creek Reach due to the hydraulic conditions that exist in this location. Now, let's talk about some lessons learned in a scary story about utilities. During the design process, we requested utility locates throughout the project area to identify potential conflicts to avoid. And prior to the start of construction, the contractor, CEI, also requested utility locates on 2 separate occasions, which showed we should be all clear. However, when we started to build the ungrouted cascading boulder drop structure, for good measure, the contractor called for one more locate. This time, two 24-inch high-pressure gas lines were identified for the first time, and it just so happens to be directly beneath and in conflict with the proposed sheet pile wall. Stantec, Olson, and CEI worked quickly to develop a field design change to move the drop structure downstream by about 30 feet and avoid the gas lines. Now, let's zoom back over to the West Tollgate Creek channel and talk about some of the permitting challenges. As discussed earlier, both of these tributaries had experienced significant downcutting and abandonment of the existing floodplain. However, the existing sinuous pattern of the West Tollgate channel was essentially locked into place. This is typical and predictable channel evolutionary response to changes in watershed, which is represented by stage 4 in the channel evolution model, where the channel is actively working to create a new floodplain at a lower elevation. This stage can take tens or hundreds of years before widening enough to create a new stable floodplain. Additionally, the stable planform of the new floodplain would have been much less sinuous than pre-modified conditions. Our design fast-forwarded the channel evolution process to the equilibrium stage by establishing a slightly confined and less sinuous floodplain. While this is the most stable form of channel given the current conditions, the U.S. Army Corps of Engineers initially would have required mitigation for the restoration because of a reduction in stream length. Although the stream quantification tool was in its infancy and hadn't been fully adopted in the state, we convinced the Corps to allow us to use the beta version of the SQT to quantify impacts and/or functional uplift. Stantec teamed with ERO Resources, who led the permitting process, to use the SQT to show that although the existing stream length was reduced by over 2,000 linear feet, the project still showed an increase in functional feet. And in fact, this was the first project in the state to utilize the SQT in a Corps individual 404 permit. Now, let's look at the bioengineered bank protection structure called a wood toe that was used throughout the project. This structure utilizes locally salvaged logs and woody debris to form a stout and roughened outer bank, which slows water down around the bend and mitigates lateral bank migration. A subbase of logs are placed along the toe of the outer bank at the pool bottom elevation. These logs are buried into the bank and covered with smaller woody debris and compacted with fill. Live cuttings of willow whips are placed on top of the logs, and then a series of soil lifts are installed up to the bank full elevation. The use of live cuttings provides rapid revegetation, and the root mass of the willows keys in the structures and provides long-term resilient stability. Now, let's zoom up to the East Tollgate Creek Reach 1, which was the upstream-most reach of this project and located adjacent to the Delaney Community Farm. Of all the existing channel reaches on this project site, this area was in relatively decent condition. A small and semi-connected floodplain existed throughout most of this reach, as well as stands of mature cottonwood trees. However, the pre-project floodplain model showed that conveyance capacity of the existing corridor could not contain the 100-year discharge. A portion of this modeled flow spilled over the western valley through the Delaney Community Farms and potentially impacting the Peninsula townhomes, which can be seen in the background. The proposed design increased the flood flow capacity by excavating a wider and better connected floodplain corridor, thus eliminating the spill flow and risk of flooding. A comparison of the existing and proposed flood extents with the proposed shown in blue showed the results of the increased conveyance capacity. Because of the proximity to the historic Delaney Community Farms, the design in this reach was optimized to work around and preserve as many of the mature cottonwoods as possible. Any trees that required removal in order to achieve the necessary flood conveyance were repurposed into the bioengineered bank and floodplain stabilization structures and used in the log riffle. The log riffle structure was built out of natural materials utilizing alternating log veins with some void-filled riprap and excess brush as backfill. The log vanes serve as 5 distinct grade control points to spread the riffle drop over a longer distance. This structure is installed starting at the downstreammost vane, with the vane slope in the upstream direction. Filter fabric was used to prevent piping beneath the log vanes, and we utilize brush fill along the upstream face of the vane to help fill the voids prior to the placement of riffle substrate. The natural variability of the log surface provides a natural-looking channel bottom that blends into the adjacent area. The completed structure creates a stable channel with a diverse bed form and meandering low flow. And with that, I'll hand it back over to Kate.
Thanks, TC. That was some really awesome footage. So to wrap up, I'd like to come back to the original objectives of the project. As you might recall, we had 4 main project objectives. The first, to reduce in-stream sediment loading, was met by stabilizing the stream banks and preventing further downcutting and over-widening of the channel. By increasing the floodplain conveyance capacity of the system, we were able to meet the second objective and remove 37 homes from the 100-year flood zone, thus alleviating the flooding risk to adjacent homeowners. It's also worth mentioning that we were able to save the client time and money by combining the channel work with the concurrent trail work into one clomer instead of 2 individual clomers. The overall channel function has been greatly improved, not by returning the channel to its original pre-development geomorphology, but by advancing it to a new equilibrium state. This allows for the proper movement of flow and sediment through the channel that we predict will be maintained as a stable channel into the future. And finally, public access was improved by incorporating the regional trail, which adds connection to over 10,000 linear feet of trail, and also by adding in the crushed gravel paths through the reaches. We hope that these smaller access points invite the people who live along this channel an opportunity to connect with the creek that runs through their backyard. Now, at the end of the day, one of the main questions is going to be, will this hold up over time? As we mentioned in the introduction, construction was completed last year, and we haven't had any major storm events since then. We have seen some smaller rain events in the 1 to 2 year range and can see detritus and natural debris depositing on the floodplain in the way that we intended it to for those storm events. So far so good. And I hope to report back after this has seen a little more time that things are still going great. I'd like to thank everyone who was involved in this project. Of course, the client, City of Aurora, the Mile High Flood District, our design partners, Olson and ERO, and the project contractor, CEI. This project won the 2020 H2O Project Award from the Colorado Contractors Association, and that is the result of all the hard work everyone on this team did and the great job they produced. Thank you for listening, and I'd like to open it up for questions.